Welcome to a lesson with Dr. Powell. Let's take a look at how we can, from matrices, actually see what the connected components are, not just how many of them there are. Let's look at a very simple example, an undirected graph here. And let's look at its adjacency matrix, thinking this is 1, 2, 3, 4. Okay. So what comes into 1 is from 2, what comes into 2 is from 1. What comes into 3 is from 4, and what comes into 4 is from 3. Notice how this matrix is symmetric about this diagonal. Now, let's replace each diagonal, or what's on the diagonal entry, with how many edges touch vertex 1. But I'm going to make it but then we're going to make that negative. So notice that there's one edge that touches each vertex. So I'll put a -1 in each entry, first, second, third, fourth, going down. So we take negative how many edges actually touch that particular vertex. Here, they're all the same in this instance. Notice something about this. If I take the sum of each row, I get 0. And that's because the diagonal actually, what it does is it takes the sum of how many edges each thing touches, and then it just negates it. And so if you add it up, you just have 0. Okay. Now, if I take a look at this in particular, you notice we kind of have this basic idea here. If we just looked at these right here, this is a complete closed piece of the graph, because if you just sum up the first two entries here and here, you end up getting 0. In other words, everywhere that comes out and back, you get something, and you're not going out to something else here that we've accounted for. So that would be fine. But we're all kind of enclosed in here. And you notice that if I just put 1, 1, 0, 0 into a map right here, defined by this matrix, and did a multiplication, I'd end up getting 0 as the 0 vector, an output of that. And so this is actually in the kernel of this matrix. Likewise, 0, 0, 1, 1 is in the kernel. And the kernel actually is defined as being sums of multiples of these two guys. And so you get the dimension is 2. And in particular, these are in the actual actually define the are a basis which define what the connected components are, first 2 and second 2. Now, if we were to find let's consider what happens when we find the Smith normal form of this, and let's consider what kind of column operations we use. First of all, let's go ahead and we're gonna apply the column operations to the identity matrix here. So first, let's add these rows together to just get -1, 1, 0, 0, and then notice we get a 0, 0, 0, 0. Okay. And then if we add the second 2 or the last 2 down there, we end up getting, and maybe replacing the bottom one with it, get something like this, 0, 0, 0, 0. So we end up getting something like this. Now let's just do now we're in line for some column operations, and we're going to do those same column operations over here. So first, why don't we just switch these two right there? Switch the first 2 columns. So we have a 1 and a 1, and that would make that a plus and a minus. That switches the sign. Then it's just take this column and add it to that column, would make that 0. And process, so we take this column, add it to that column, we'll put a 1 right there. Okay, great. Next, let's kind of do something here. Let's take this column and add it to that column. So this column and add it to that column and put a 0 here. Okay, now let's just kind of rearrange things a little bit with columns a bit. So in doing that, in fact, we don't even have to rearrange. Notice how we have 2 0 columns here. These 2 0 columns are the positions that correspond to the kernel here. Notice what the kernel is. Kernel is this, or this is a basis for the kernel right here. Notice it's exactly what we desired. We just were able to find what the connected components were of this graph by looking at this adjusted adjacency matrix, where we took negative of the edge incidence of each vertex down there. This particular matrix is called the Laplacian. Another way to get the Laplacian is take the transpose of the incidence matrix and multiply it to the incidence matrix itself, and you also can arrive here at Laplacian. Kind of a fun idea to be able to get this and use it, and looking at the kernel in order to figure out looking at the kernel to figure out what the actual connected components are. Thanks for watching.